Hey everybody, in this next video lesson, we're going to talk about decomposition reactions. Now, a decomposition reaction can be thought of as a reverse combination reaction. Where combination reaction takes two things and combines it in to make one, a decomposition takes one thing chemically bonded and splits it up into two separate substances. So a decomposition is the opposite of a combination reaction. Like I've done with some of my other videos, I'm going to splice in at this time a little bit of a video that I recorded for another class. And when I'm done, I'm going to come back and talk about the special cases you see here on the bottom. As a reminder, a decomposition reaction has one complex reactant and two simple products. Essentially, you're going to take an ionic substance and split it up into its metal and nonmetal. The way I would describe a predicting products of a decomposition is take the AB and split the AB apart and write each alone, meaning you write, even if A had 2 or B had 2 on the reactant side, you write it as alone, singular A and singular B on the product side, and then separate it by a plus sign. Then, take each element and check for diatomics. They are as follows: H2, N2, O2, F2, Cl2, Br2, I2, and At2, H, NOF, and then all down group 17. These are elements when found by themselves come in pairs. Some examples of decomposition reactions that I've listed are Ki, Al2S3, and CaO. So I'm going to take each of them and separate them singularly and put a plus sign between them. So I'm going to put K with I, aluminum with sulfur, and calcium with oxygen. Notice I took each and I split them apart and wrote a plus sign between them. And then I go back and check for diatomics. Now I'll tell you this. A metal will never be a diatomic. A cation cannot be diatomic unless it's hydrogen. So if it's a metal, it stays as monoatomic. In example, aluminum and calcium. But these other ones, these anions, I double check. Now, I look over here. Iodine is one of my diatomics, so I write in I2. Now, sulfur is not one of my diatomics. It's not on the list over here on the right, so I don't need to worry about it. Now, oxygen, once again, is. And so I make that diatomic. And that's as simple as that. Decomposition, you split up the ions, separated by a plus sign, and check for diatomics. All right, now let's talk about these special cases that you see in the bottom. Now, most decomposition reactions you'll see are just basic ionic substances that you see like these at the top and split into individuals. And in that case, you just separate them with the plus sign and check for diatomics. But there are a couple of special cases where we have larger and more complicated compounds, and you need to know these three special cases and how they decompose. So the first one we're going to talk about are carbonates, metal carbonates specifically. The metal carbonate will always break down into the metal with an oxygen and carbon dioxide. For example, lithium carbonate will split up into lithium oxide and carbon dioxide. The next one, the metal chlorate, is going to break down into metal chloride and oxygen gas. Now this is separate or different than the decomposition of the carbonate. Both of these contain oxygen in the polyatomic ion, but they do not separate or decompose in the same manner. Pay close attention. A chlorate will break up into the metal chloride, balancing the charges here between magnesium and chlorine, and oxygen gas. Finally, a hydroxide, or what we refer to as bases in the business of chemistry, will always decompose into a metal oxide and water. And so when you take something like sodium hydroxide and split it up, it will make sodium oxide, Na2O, and H2O. Well, that takes care of this video lesson on decomposition reactions. Thanks for watching.